Okay, let's get started now. First of all, any questions about anything from past classes? Any questions about anything going on in the world? Last year I taught a course on computational finance last semester. And so the question of what was going on in the world was very interesting and relevant. Here I guess what's going on in the world usually isn't that relevant. So anything interesting going on in the world? Probably not. Okay, how many people, let's go through the list. From last week's problems on sorting, how many people got all four? Raise your hand if you got all four. Okay, how many people got three of them? Okay, how many people got two of them? And how many people got one of them? Okay, is there anybody who got none of them? Okay, so that's good. So we're making progress on that. Anything interesting on any of the problems that came up from last week that anyone wants to talk about? You? Or what happened? What interesting? Anything? The question is, we talked. Anything that anyone wants to add from their experiences on these problems since our last class?
About something that the whole problem about something.
Yeah, four problems about sorting.
I think you it's I have nothing to say.
Nothing to say? Okay, good. Okay, there's nothing to say and he said it. Okay, good. Anything else about that? Okay, so this week's problems are going to be on arithmetic, mostly arithmetic and algebra. Yes, question?
Just talking about the question last week.
Yes, what about that?
About the CDV2 question.
About the what? CDV2 question. Yes, what about it?
The UBA description has one line different from the programming challenges. I think programming challenge is not specific enough. Because if a record costs zero money, the record should not be printed. The UBA just had this line, but the
okay, so you're saying that there was a difference between... Okay, so you were complaining about something on the description of the CD... whatever it was. It's the toll problem. How many people got the toll problem working? Raise your hand if you got the toll problem working. Did it work on both? If you got it working, did it work on both judges? Raise your hands if it did. Okay, is there anybody who for the toll problem, it didn't work on both judges? Yes. Your toll problem worked on which judge?
Oh, both of them are actually.
Oh, it failed on both of them.
Yeah.
Okay, if it failed on both of them, that's fine. If it worked on both of them, that's fine. I was concerned about it's better, it's fine. If it was, the ones I was worried about were the ones that didn't work, worked on one or the other. So you claim that there was a difference between the two judges?
description.
The description. And if so, what I will say is I probably edited it and made sure it didn't change the solution. Change the way it was being judged. So mine made it simpler, presumably, than the one. The programming challenges one was presumably simpler than the...
No, the UBA charge is more specific than this in this question.
Okay.
It said if a record costs zero money, then the record should not be printed. But the programming challenges did not have this line, so
I see. Okay. Interesting. Okay. But anyway, the fact that it worked leads us to believe it's not a problem ultimately. Okay. Any other questions about any of this? Okay. So this week's problems have to do with arithmetic and we're starting to get into problems having to do with arithmetic. And the standard programming contest problems having to do with arithmetic, I would say, fall into two categories. One is that they are about how do you do long arithmetic, okay, the mechanics of doing actually big number arithmetic, because that involves some interesting interplay of programming and mathematics. The others involve clever problems about the properties of arithmetic, okay, and so a couple of the every week we're going to look at a different subject. Today we're going to look at, basically, this week we're going to look at things having to do with arithmetic. Later on we're going to talk about number theory, where there are some other properties of things related to arithmetic. But today I think we're going to stress mostly what I'll say are the programming level aspects of dealing with long arithmetic, rather than the stuff we'll talk about in number theory. How many of you have ever built a library for doing infinite precision arithmetic, or very large precision arithmetic. Okay? If you have implemented large precision arithmetic, hold your hands. Raise your hands. Okay? How many of you have never built a library for doing long precision arithmetic?
Use library.
Well, by library, have ever... we're going to talk here about how you do addition, subtraction, multiplication, and division with big numbers. That's going to be a part of what we're going to deal with. Very big numbers. I'm just curious, how many of you have done that before? Written it. Written it meaning that you have implemented it. How many of you have implemented a big num package? Raise your hands if you implemented a big num package. Raise your hands if you never implemented a big num package. Okay, that's good. Okay, that's what we're really going to be talking about today, is about implement big number arithmetic and how you do it. So one question is, how big is a big number? Okay? How long is... Actually, those of you who own computers, how many of you own 32-bit computers? Raise your hand if you own a 32-bit computer. How many of you own 64-bit computers? No one will admit to it. How many of you ever owned a 16-bit computer? I am old enough that you did. Why did you own one?
That was about 17 years ago.
Okay.
Wow.
Okay, and some of you maybe say, oh, I wasn't alive 17 years ago. Well, I was alive 17 years ago. Actually, to be honest with you, I actually have programmed on an 8-bit machine. Okay, if I go back far enough. But basically, typical PCs today are still 32-bit computers. Okay, and what that means is that the basic integer operation still basically works on a number that is basically plus or minus 2 to the 31. Why is it if you have a 32-bit computer, do the numbers go up and down to go to 31, 2 to the 31 rather than 2 to the 32?
Of course, the most significant bit is the sign.
Because basically, if you go plus or minus, that means that the equivalent of the first bit is essentially a sign bit. And that basically doubles. You have both positive and negative numbers of that magnitude. So that accounts for the 2 to the 32. So what this means, if you think about it, is that you can safely count up to 2 to the about 2 billion. That's right. Those are hundreds, thousands, millions, billions. You can safely count up to about 2 billion without worrying about your integer and whether you will overflow. Now, is a billion a large number? Okay. Who here thinks a billion is a large number? Who here thinks a billion is a small number? Okay, you think a billion is a small number. The answer, of course, it depends upon your application. You know, I think when I wrote the book, I said that the United States national debt was about 1 billion pennies. So that was about the limit of it. But now we're talking about deficits on the order of trillions. Okay? So, you know, so billions may no longer be large numbers. If you wrote a loop, this is actually an interesting question. If you wrote a loop on your machine, count for I goes from 1 to a billion, how long do you think that will take for your programming language? Okay.
10 seconds.
10 seconds. Okay? So, you know, by that definition, counting a billion things is still now an operation on the order of seconds. Okay? So 32 bits is a big number, but not a huge number. If you can get up to 64-bit integers, okay, then basically you can start to talk about very much larger numbers. What is this? This is hundreds, thousands, millions, billions, trillions, probably quadrillions, I think, if I know what I'm talking about. And then things I don't know how to name. Okay, so on a 64-bit machine, you certainly can count to very large numbers, except you probably couldn't count on it. Okay, because again, if it's a billion times 10 seconds, a billion times 10 seconds means the loop for I goes from 1 to the largest integer would take years and years to run. Right? Does everybody get that? So 64-bit integers or 128-bit integers are very large. Okay? You can often get, I guess in C++, long means what? A 64-bit integer? What does long mean in C++? What? Well, there's int, there is long, and there is long in different languages. So long is 64 bits. Okay? Long is 32 bits. What is int? 32 bits. Okay? There was a time when, integers were smaller than that. Okay? So, if you need to work with very large numbers, you sometimes need to push the limit of these things. Okay? And that's where unsigned integers sometimes come in. If you define an integer as unsigned, then I guess you get an extra, you double your range of integers because it'll count higher. Has anybody ever used unsigned integers before? You did, okay? And okay, that's interesting. So it does work if you have a reasonable compiler, and that's good. Okay, any questions about that? Now, you might think that you can get larger numbers using floating point numbers. Because floating point numbers, you can easily get a number, of the form, floating point numbers, you have a certain level of precision in what I think of as the value part of it. And then there's a certain level of precision in the exponent. Okay? So you can have a number, something like 5 point, what's Avogadro's number? Does everybody remember Avogadro's number from chemistry? What was that? Does anybody remember that?
2.222, no, 6.22 multiplies 10 raised to the power of
23, if I remember correct. Right? So if you wanted to represent Avogadro's number is represented by, it's a large thing. It involves 23 decimal digits. Okay? But the way that it's represented is a relatively low precision. I think they call it the mantissa. Is that what it is, I think? The mantissa is the front part, the real part of this thing. And you multiply it by an exponent. You can get very, very large numbers by just using a larger exponent. To the point where, depending upon how floating point numbers are implemented on your machine, the exponents might very well go up to the, does anybody know how big on a typical, let's say, machine these days, how big an exponent, what kind of floating number range you can implement? Okay? It doesn't really matter for us, but the only issue here that's important to note is this is going to be unbelievably large. You have an unbelievable magnitude of numbers range that you can represent in floating point. The trouble is you get a finite amount of precision. Because what this says is you probably get something like 10, 15, 20 decimal digits of precision with an exponent then that can range wildly. Okay? So if you try to deal with, you can't use floats or doubles. Okay? If you really want an exact value on a large range of numbers. If you want an approximate value on a large range of numbers, this is what floating points are good for. Any questions about floating points or anything like that? Okay, good. So what I'd like to concentrate on today is the problem of building a infinite precision arithmetic package. So I'm going to be doing integer. Let's think about it. I'm going to want to represent integers that are not just long, but unbelievably long. Let's say we want to have 100,000 decimal digits. Let's say we want to have 1,000,000 decimal digits. Okay? That's the kind of long that we'd like to talk about today. Okay? So my question is, if you wanted to implement a long package, what kind of data structure might you use to represent an integer? Okay? What was that? I heard someone? Array. Array of what? Okay? I heard integers. Is there anybody else want to say what they want it to be? You say arrays of long. So what are our possibilities? If we want to represent an integer, an arbitrarily long integer, one possibility is to use an array of digits. We could have this be an integer, in which case this would be 4 bytes long, right? We could have an array of long longs, in which case they would be 8 bytes long. Okay? Anybody want to propose anything else?
Array was maybe around 60,000 or so. Since the problem is an array is normal is that when you do multiplication, there will be overflowing issues. So it's not easy to handle it.
Okay. So what I'm hearing was, wait, was I hearing about how long my array should be? Is that what you mean?
8. I mean, an array of integers with the limitation that each integer can only represent 16 bits.
Okay. So the question here that comes into it has to do with the following. Okay. The other I'm hearing integer as candidates. I'm hearing longs as candidates, or long longs. Another one I'm going to propose are characters. Okay. Because on my particular package, I did it that way. Although there's pluses and minuses to doing it this way. Okay? What does the issue here come down to? I think that when you're representing an integer like that, what you want to do is to somehow represent one quote, digit in each cell of the array. That is really what the idea is. Okay? And the question is now, what base are you going to be doing your arithmetic in? Okay? If we're going to do our arithmetic in base 10, that would mean that we would be holding one digit value, a value from 0 to 9, in each position in the array. Does everybody see that? And if we do that, does it matter whether we use long, long, or int, or jar? We're going to work in base 10, okay? Then we're only representing numbers from 0 to 9 in each spot, okay? It is actually wasteful to use these long, long integers. Does everybody agree with that? Now the question is, should we be working in base 10 or not? Okay? Who here would want to argue for base 10? Okay? Nobody.
It's also a good idea because if your program is based on 10, then it's very convenient to output the answer.
Okay, so the advantage of dealing with things in base 10 is that it is ultimately going to be read by a person. People have 10 fingers, okay? And for that reason they count in base 10. Is this right? Okay? So somehow an elementary, one operation you're going to have to do if you're going to work in outputting this number to people is eventually converting it to and from base 10. So one good thing about working in base 10 would be that it'd be very simple to do that. Does everybody agree with that? What would be a bad thing about doing it in base 10? Okay? Is base 10 the right thing to do it in? Okay. What is it maybe a bad thing to do it in? What? Computational efficiency is taking a little bit of a hit here. Okay? Why is computational efficiency taking a hit if we do it in base 10?
Itself is doing a binary form when you're doing arithmetics, and if you split it up and this and kind of going around
Okay, so the problem here is that ultimately you're going to still be trusting the computer to do basically adding your digit level arithmetic, doing your digit level addition and multiplication and subtraction. Does everybody agree with that? And the trouble is that not the trouble. The great thing about your computer is that because you have a 32-bit computer, it's able to add and subtract in one step numbers up to 2 billion. You're somehow not using all the power of the hardware. If only you're going to be giving it problems of size 2, size 1 digit. Does everybody agree with that? So from an efficiency point of view, if we use a larger base, okay, we will be able to represent numbers in smaller numbers of digits. Does everybody see that? Think about it this way. If, computers have only 2 fingers on them. That's why they count in binary. Okay? And they need 32 bits to count numbers that we use in billions. How many digits was there in billions? Okay? Hundreds. Thousands. Millions. Billions. Right? So that says that in some sense 32 bits is the same as 10 digits, right? So our numbers are 3 times shorter than they are in binary. And if we could now use, instead of base 10, a much higher base, the numbers will be even shorter. And shorter means less carry operations, less of the slow bookkeeping that we have to do. Okay? Any questions? So what would be the right efficient size to make our integers if we wanted to really make a high efficiency calculator? Okay? What would be the right size? We have a 32-bit word. Okay?
60-bit.
Wait, you're saying you want to use 1,000. Okay, so let's look what he's doing. There's a couple of different ways to do it. One idea is you're going to do a base 1,000. 1,000 has the property, I guess. Wait, base 1,000. Is it base 1,000 or base 10,000? What are the numbers? What? 1,000. So the numbers are going to go from 0 to 999 in each digit. Is that right? Now, why did you pick 1,000?
Because I give you when 2 numbers over b, a by b, and it's not over 1 million, right?
Okay.
But when I implement the multiplication, there are maybe many A by B, they are added together. Then if I use 10,000 instead, the sum of this multiplication, the product
Okay.
over the in.
Okay. So the question here is, he doesn't want to, the reason he wants to pick something like 1,000, base 1,000, is that we may have to multiply at some point 2 digits together. Multiplication involves multiplying pairs of digits the way that people typically multiply. So a 999 times 999 would generate a number potentially as high as 1 million. And this still fits in an integer to be dealt with. So this is still comfortable. Now the question would be, can we get higher? Okay, if we made it 10,000. Now we're up to 100 million. And so I would think with 10,000 you could still do this safely. Okay?
Yes, but I implement the multiplication in a way that, for example, the first digit of the product, they are sum of.
Okay, anyway, the idea of, but why 1,000? Let's still think about it. What would be the maximum amount you could do if you wanted to make this as efficient as possible? What would be the argument? What would be the size that we would want? What?
10,000 if you use int.
10,000, you're saying if you use int. Actually, that's not true if you use int. Okay.
65,560.
say 65,000, something like this then. What would that be? I claim that if you're worried about multiplication, what you really want is the square root of a 32-bit number. That's really what I claim the maximum is. It's the floor of the square.
That's not convenient.
What?
That's not convenient without.
Okay, but now that's not convenient when outputting it. So what's good about the 1,000 idea, or the 10,000 idea, is it is more efficient than the base 10 idea, while still keeping it looking like a base 10 number, so it's easier to input and output.
Yeah.
Okay?
That is actually a base 2 number, actually.
What?
I mean, that number is actually a base 2 number. When you do it. It's 2 to the power 32, so 2 to the power 16. So if you want to do that way, that means you are doing base 2, not base 10.
Well, okay. So the question is really, we can either do it in base 10 totally, or do it in some other base where it's larger and still relatively easy to convert. Or we could do it in the largest possible base and then convert, right? For maximal efficiency, this would probably be the right answer, okay? For, if you're really building a high-performance calculator, if you're trying to do something quick and easy, this is probably the better idea. This is probably a good compromise, I would say, okay, in the context of what we're doing here, okay? Any questions?
I want to
Yeah.
further explain what I said just now.
Yeah,
Can I write on
you
the
may
board?
certainly come up here.
I mean, if it's based on 10,000, for example, there are many. Suppose A is equal to then this is based on 10,000, and B is the same number.
Yeah.
And when I do the multiplication, I implement like this way. For example, this one multiply this one, the product will install here. Will install here.
Okay.
And this one multiply this one, it's also installed here. The same base, they will add it up at first. They will add it. If the size of the digit of the length of digits is very long, for example, there are 1,000 digits,
Right.
and the maximum could be these numbers where maybe more than.
Okay. Let's say what I would say is we agree that, but I think what we're agreeing is that the closer we push this to the limit, the more careful you have to be about overflows on your immediate operations. Okay? And that much, let's say, I will agree with. Okay? And the question of where you come down in engineering something like this. You know, how much of a difference is it, though? Let's think about it. How much faster will his base 1000 version be, potentially, than my base 3 version, my base 10 version? What? About 3 times. Okay? So the issue really is one of how much effort do you want to do to save that factor of 3 in storage and running time, right? And it's probably not worth getting heroic about it. Okay? Any questions? Yeah. Unless you're really trying to write the...
I do not clearly see a reason about why you need to use the storage space of B, or I mean, each time when you do the multiplication, we do not need to.
Okay, this is what I'm going to say is an engineering issue.
Yeah.
The question of whether you do 10,000, can it be work for 10,000? Yes. Can it work for 100,000? Probably. Can it work for 1,000? Yes. 10,000? Yes. 10? Yes. Okay? But there's different speeds and different complications. And there's some engineering issue here. Okay? Any questions? I would like to think that GNU's big sum library uses this. I would like to think any programming contest solution banged out in an hour or two uses this or probably this. Okay? Probably this. Since you're only saving a factor of 3, it might not really matter usually. Be worth saving the extra bases. Any questions? Okay. Is an array of digits, though, the right idea to it? We talked about the base. What about the idea of an array? Is an array the right structure to keep for the bits to get the digits together, or would there be some other kind of structure we could use?
I think linked list is kind of better.
So we could use a linked list of digits instead. That the number, this is the head of it, the number. First of all, if we have a linked list of digits, do we want the pointer to the front? Let's say our number is 2009. Would you want your linked list to point to the beginning or the end of the number?
I think the double linked list is.
What?
I think post is fine. Of course, we want to do it from.
So you're saying you might use a doubly linked list with the numbers 2009, and you point to the head and you point to the tail, basically, right? That's one possibility. Is that good or bad? What's good and bad about linked lists?
When doing addition or subtraction, it's okay, but if we're doing multiplication, we need random access.
He says multiplication would help with random access. I would say you could always do anything anyway, okay? When I ask me where do I come down on linked lists versus arrays, okay? Recognize that what arrays do is they provide you the freedom to use space where you need it. They don't, linked lists do not save you space, okay? If you're only going to be working with 2 huge integers, okay, then it's probably not going to matter very much. Because in a huge integer, if you're representing it by a linked list, then you've still got to pay the cost of the pointers, which doubles the size of the number that you're dealing with, right? If you have a small number of integers that you're representing, it's probably easier to use an array, okay, of integers, digits. The place where linked memory structures is useful is where you don't know where you're using the space. Okay? And if you say I'm only going to have 2 big integers, I'm adding one, reading them in and adding them and printing out the answer. Well, you know where you're using the space. Okay? If on the other hand you were going to have maybe 100 integers, maybe 1,000,000 integers in your program, they're allocating different amounts of memory. Depending upon the size of the integer would matter. That's where dynamic memory would help. So I would probably come down on the side of using arrays for this. And I would put probably some kind of an upper bound. If you had 100,000 digit integers, that would still be an array of only 100,000 characters in my implementation. Okay, and you certainly have the memory for that kind of thing. Any questions about that? Okay, fair enough. Actually, are there any built-in long precision math libraries in C++? Everybody here is a C++ person. Has anybody ever used a math library in C++ for doing long precision integers? Okay? The good news is that there is one. GNU has I think it's called I don't know if it's a BigInt package or I don't remember what the name of it is. It's in my book, actually. I could look it up. So the good news is that there is a C++ library for high precision integer arithmetic. The bad news is it's not part of the standard library. Okay? So if you're sitting there in a programming contest trying to use it, you can't do it. If you're sitting there outside in the world trying to do something like count the number of pennies in the national debt, then it's available to you. Okay? Now Java does have a built-in long integer package. Okay? So if in fact if you encounter such a problem and you know Java, okay, my students would for example do this some of these problems in Java to avoid, because they could take advantage of the built-in library. Any questions? Okay, so how would I implement a big num? Here was my idea of how I implemented it. Maybe let's show you how I did it for my package. And then let's kibitz about it and complain whether it's right or not. I represented an integer as an array of digits where I had a maximum number of digits. Perhaps this would be better off done as a dynamic array. In fact, if you wanted to worry about, let's say, getting the advantages of the fact that the integer will not take up space unless it's using all the digits, you might make that a dynamic array. But I represented it as basically a structure on three things: an array of digits, a signed bit explicitly, and an index to tell me where the highest order digit is. Because if I'm going to be dealing with 100,000 element arrays, I could figure this out by scanning from right to left and find the first place that was not equal to 0. But that would involve initializing the whole thing. That would involve scanning the whole thing. It's easier for me to keep track of the digit. Any questions? So how would you do addition in high precision arithmetic? Let's think about that. Okay? If I have an array of digits here and an array of digits here, A and B, okay? How would I do arithmetic? Okay? Any ideas? What would be the basic procedure to do arithmetic in this high precision way? Okay, I don't expect anybody to be able to read it yet. Okay? Any questions? So if we have A, this is going to be the low order bit. If I have if I start at the low order bit, how am I going to go do the arithmetic? The basic idea is I should add this to this, and then add this to this, and then do what with the sum? Suppose this was 7 and this was 13. No, this was, remember I'm doing it in where the digits are 0 to 9. This is 7 and this is 6. What should I do? What is the basic mechanism I should do?
Get 12 plus 1 is the sum of 7 and 6, and the others can.
So what I need to do is to somehow add them together to get 13. But then break them up into the two digits somehow, 1 and 3. What is the right way to, because this is going to really be something that's going to have to be part of a carry. Does everybody see that? What is the right way to take 13 and break it up into its carry and its actual last digit? How do I find its last digit? Somebody with a hand who doesn't talk much. What? Take it mod 10. If I took it mod 10, it will give me the remainder of mod 10. That would be the digit that goes here, right? And how would I get the higher order digit? Okay? Basically what I could do is I could take my number and divide by 10, right? If I have 13 divided by 10, now I've got my other digit, right? So the basic point that I'm going to be doing here is to take this digit plus this digit plus the carry, and that's what's going here, and I'm going to mod it by 10 to put the number there and carry it out, figure out what the next carry is. When is that wrong? Okay? So adding up the digits like this make a lot of sense if I'm adding numbers up, except for one thing. When would that be wrong to do it this way? Okay? What if one of these was a negative number? Okay? If this one had a sign bit that was negative and this one had a sign bit that was positive, this would be the wrong thing to do. Does everybody agree with that? Now I add it up. I mean, that's this. You know, what's this going to be? This is really going to be -1. Okay. So how do I deal with addition when I have negative numbers? It really becomes subtraction. Does everybody agree with that? So if you look at my procedure for dealing with addition, I have a function that takes big numbers A and B and adds them put the sum in C. The first thing I do is some sign bit manipulation to take care of which cases. What are the cases that are interesting? Okay? If the sign bits are the same, okay, then I can do addition the way that I normally do it. If they're both positive or both negative, I can then just do the addition and set the sign bit of C to be the same as the sign bits that they both have. If they're both negative, the sign bit of my number is going to be negative, otherwise it'll be positive. Otherwise, if there's a difference, I've got to convert it to a subtraction problem. And how is the right way to do that neatly? Let's think about it. Suppose I am giving you these problems. How would I then reduce this to a subtraction problem? Okay? It would be basically, I'd have to put the positive number minus the absolute value of the negative number. Is that right? And that's pretty much what I do here. I take the absolute value by setting the sign bit. I then subtract it, and then I reset the sign bit. Okay? Once I am done. Okay? Any questions? Actually, though, okay, let's say yes. Okay, I have to then reset the sign bit. Any questions? Okay, so what is my basic way of doing the addition? It's basically down here. I find the last digit to the right that I worry about is the larger of the last digits of the two things that I'm adding, because I'm doing it on a character by character basis. Basically what I did is that the basic sum is carry plus the first digit plus the digit of the first number plus the digit of the second number. Mod 10 for the digit, divide by 10 for the carry, and keep going. And I found I needed to do something to justify zeros. Sometimes in the course of these things, I have to adjust what the last digit is. Because in certain operations, like a subtraction, for example, suppose I were to subtract, add 10 and minus 15. The number here is going to really come out to be minus 5. These numbers both had 2 digits. The sum at the end had 1 digit. I've got to find do some adjustment to correct for that. And that's what I meant to do with my zero justify. Any questions about addition? Addition, I think, is pretty straightforward. Okay, and the sign bits we talked about with that. And here is how I did my justification. Basically, I looked for the first non-zero digit, okay, and then set the appropriate sign bit. And in fact, had to deal with something because sometimes, if you're not careful, you could end up with minus 0, okay? And I normalized minus 0 to 0 for convenience. Any questions? Now, how would you do subtraction? I know you can't see that. I don't need to look at that now. How would you actually implement subtraction? Okay? Any ideas? Okay? Suppose I now want to do the subtraction of two numbers. What is the way that you would go about doing it? Okay? It is, if I'm going to subtract A from B, here it is A minus B. Okay? How would I do it? So one possibility is to take the tens complement and add it together. How many people here think in terms of two's complement? Okay? How many people learned about two's complement arithmetic in a class? Okay. And what class was that taught in here? That's an interesting question. When I was an old person, we didn't talk about that. What course teaches this kind of stuff?
Organization and architecture.
Okay, take an architecture class. I guess that makes sense. Okay? So what is 2's complement? Does anybody remember what 2's complement is? How would you do 10's complement?
For each digit, then 10 minus its digits, and add 1 and last.
So you're saying that one way to implement it would be, if I wanted to subtract 7 minus 6 like I have it here, let's make it a little bit higher. That's it. It's not the way I did it, but it's an interesting idea. Let's make it 87. No, actually, just for making it a... let's say it's 87 minus 58. You're saying that what I would do is I would take the second number, and it's a 10's complement that you would say you would take 10 minus that digit. Is that right?
For every digit.
So that would be that this would become, in 10's complement, a 2, and this would be a 3. And now what would you do with that?
I think this should be 1 and...
So what would taking 10's complement... Oh, wait. Okay.
It's 9 minus 8.
We want to say this is... Sorry about that. You're 100% right. That is... Wait. 10 minus...
It's 1 minus... it's 9 minus 1 is 8. 9 minus 4.
9, okay? So that would be 9 minus this. That would be a 1 and a 4. And then what would you do?
And every other digits are 9.
What?
Every other digits are 9. Every other digits are 9.
Every other digit's 9. This is 999. Okay? And this is 0. And what are you now going to do?
Add 1 to the right.
Add 1 to... Wait, no.
Oh, this is only nice complement. If I want to be the 10th complement, I should plus 1.
You add 1. Can any of you go through this example?
Okay.
Go ahead and do this. It's fun.
So I add 1 to this, this one to be 2, and add them together, ignore the overflow.
Okay? How many people follow this? Let's go. Is this a good way to do it? Let's do it. It's probably more interesting the way I did it. So let's go through and figure this out again. Okay? The algorithm is what? You took the original number, which was 78, or 87 here, and you left it there. The negative number you represented by taking each digit and subtracting 9 from it. Basically, is that right? Yeah. And that's what gave us 942. You added these together, and this came up to be, using the previous code, 91029. What?
No, one's wrong.
Is that wrong?
I think this one is...
Okay. Does anybody understand this and know how to do it like that? Okay. What? Okay. If not, we're going to do it the dumb way in a minute. Okay, this is the right way to do it if you're a computer architecture designer. And it's simpler in terms of building, the reason is because it's simpler in terms of building hardware. That probably means it might very well be simpler in terms of building software also. Okay? But logically simpler is to do it the way that we do it. Okay? And so on my package, the way I did it was the way, people do it. Basically with borrowing and subtracting. Does anybody want to try this again? Before we move on to the
I get this part wrong.
Go ahead. Show me what you do.
This is correct. Only this one. Because it's
Okay?
If it is
So let's try another one just to see what the procedure is. The procedure, we wanted to figure out what was 153 minus, let's try 772. The argument would be that we would leave it as 15230. We would convert this to 9's complement by adding 9, subtracting 9 from each digit. This would be 7.
That's 2.
This would be 2.
9, 9.
This would be 9, and this would be 9.
And plus 1 to it, because I want tens complement.
Okay, and then you want to add plus 1. So it's 3. Is that it?
Yeah.
Okay, this then becomes, we added up a 1.
8.
This becomes, we carry. This becomes an 8. This becomes a no carry.
0.
0, 1.
0, 0, 1.
0. Right, that becomes a 0. This 1 gets carried. And the claim would be that this is then right. Okay, if you know where to cut it. Does everybody see that? Okay. That's actually kind of interesting now. Okay. You did it this way. This is probably now simpler if you know where to cut it. That's really the only thing that seems complicated from a programming point of view. Okay? And if you check the magnitude of the integers that you're subtracting to determine where to cut it, it depends upon whether this number, the magnitude here, is less than the magnitude of the other one. Does everybody see that? So how would we do subtraction? Okay, the way I did it was I did some manipulations on the sign bit to figure out when was it really just integers, addition. Okay? And when was it normalizing it to a form where I gather, what do I say? I said compare if A is bigger than B. Okay? I wanted, if I was going to be doing a subtraction, once I get rid of the sign bits, I wanted my first number to be bigger than the second number. Okay? And in fact, when I didn't, I flipped my sign bits appropriately. The basic way I did it was, again, by basically using borrowing. Okay? Figuring out, what I did was I did my subtraction. I said my borrow was initially 0. I subtracted the 2 digits, then added 10 to compensate for the borrow if the value here was negative, okay, and iterated through it. But I would tend to think, if I remembered when I was doing this, how to do the 2's complement thing. Recognize I last saw that 30 years ago, okay? It would be probably doing it the 9's complement is better, okay? Any questions? Okay, how many people here believe that the subtraction using the 9's complement is better? Raise your hands. How many people here feel doing it the naive way is better? Okay, and my guess would be if you're comfortable with the 9's complement way, that's probably better. Okay, but if you're not, it's more straightforward to do it this way. Any questions? Okay, so that's very interesting. How would you compare if 2 numbers are bigger? Suppose I give you 2 numbers. What is the right way to compare whether or not one is of higher magnitude than the other? Let's say the sign bits are the same. What is the right way to compare whether, let's say the number here is 1057, and this is 1056. How would you tell which number is bigger? What's the basic procedure? From the highest, most significant bit. The other operations, remember, work with the least significant digit. You compare them lexicographically. Are they the same? If they are, recur back to the smaller digit, right? At the first digit where they differ is where there is a problem. And that's basically what this kind of thing is doing. Any questions? How do you do multiplication? Let's think now about this. If I give you two long integers, how would you multiply them? Okay? What would be the basic procedure to it? Okay? Any ideas about this one? First thing, does anybody know about Roman numbers? Do they teach people about Roman numbers here? Who knows about Roman numbers? Who here does not know about Roman numbers? Okay, on the previous problem, what was it that CD 405? What was that problem called? CDV11. Is this right? Is this what that problem was called?
Yeah.
What was that supposed to denote? That was supposed to denote a number written in the way the ancient Romans wrote numbers, right? What was that supposed to be? Okay, I believe that this is a 0, a 1, a 1, a 5, a D. What? What? This was a 500, and this was a 100. I think I believe that. The way that it worked was that this was supposed to be used to subtract from that. Is that right? So this really meant 100 less than 500, right? So this really was supposed to, I think, be the number 452. Is that right? What? 407, exactly right. Okay? And the Roman numbers were good enough for the Romans. They were able to do a lot of arithmetic with them. But the one thing the Romans never figured out was how to multiply. This is one thing I was told. Okay? And the reason why they never figured out how to multiply is because they didn't have a decimal type system. They didn't have a radix number representation. And so it would be very hard to do multiplication. Multiplication was repeated addition. The Romans could have always done multiplication by doing repeated addition. But of course, that would have been a complicated thing back then. Any questions? So how is it that we're going to do multiplication here? Okay? I think everybody would probably suggest that as the simplest algorithm, the schoolhouse algorithm. If we want to multiply 123 by 58, how do you do it? Okay? The way I am told to do it is that it's basically this digit times this, and then this digit times this shifted over by one spot. Does everybody agree with that? That's how I was told to do multiplication. Okay? And so the advantage, the way that I implemented it in here was by basically implementing the schoolhouse method. Okay? Which, if you think about it, the basic story is to do a single digit multiplication times a big number, and shifts to denote multiplying by 10, and then adding everything together. Those are the basic ingredients of my multiplication. Any questions about that? Okay? Now, if you do that, this is what my multiplication thing looked like. Okay? Basically, to multiply numbers together, I iterated through digits. Okay? And I reduced it to, actually this is kind of interesting. I have an extra loop here. Instead of doing digit by digit multiplication, I did something that was maybe a little bit sleazy. I took advantage of the fact that I already had implemented big num multiplication. And rather than do digit by digit multiplication, what I did do is I had a loop that went around the value of the digit, 0 to 9. If it was 5, this loop went around 5 times and added up, okay, the whole number and added that into what I was accumulating. Okay? So one way to have done this digit of 8 times this would have been to say 8 times 3 is this, worry about round off. Okay, put down a 4, carry the 2, and then implement that. Instead of doing the digit by digit multiplication using multiplication tables, I did it by repeated addition. Now, why is that efficient or not efficient? You say what? You say it's efficient. Why is it efficient?
It's efficient in the whether you're doing two addition or multiplication.
Okay, maybe. I would say that it's inefficient in that I am doing a loop here. I'm doing repeated addition instead of multiplication. Okay? Repeated addition is very, very slow. Except that I'm only repeating up to a digit's worth. Does everybody see that? Because I used a base 10 number here. My digits value is 0 to 9. This loop is only going around a constant amount of times each time. Does everybody see that? If I had been using a larger base than 10, it would have had to go through the loop potentially that many, that many times. Okay? And in particular, if I had been using something like a 32-bit, a 16-bit base, this would have gotten to be very inefficient. Okay? But because my digits are a small constant, looping around that many constant times didn't matter. Okay? Any questions? So my method here didn't involve knowing any multiplication tables for digits, or even using the hardware multiply. Okay? Any questions? I don't say this is necessarily the best way to do it, but it was the simplest way that I could do it. Any questions? What is the complexity of multiplication? Suppose we do digit by digit multiplication. How much time does it take to multiply two n-digit numbers? Okay, it's n squared. Does everybody see that? Because what you're really doing is you're taking, in some sense, again, it's n squared if you see it. Basically, you're going to be doing a shift. You basically have something like n rows. Each row will involve n interesting digits. It's an n squared computation. Does everybody see that? What does it take to do multiplication by repeated addition of two n-digit numbers? What? N cubed? No.
Multiply by digit, the base digits.
Okay. I believe that it would take, then it becomes, I believe if you've got, depending on what the base is, I believe it becomes a b to the n operation. Okay? Let's think about this. You're doing repeated addition. If I have one digit that is n digits long, it's actually probably something like n times b to the n. Why is that? What is the number that you can represent in an n-digit number? What? Basically, it's a number on order b to the power n, right? Maybe b to the power n minus 1 or something like that, right? So if I am doing it by take this number, the first number, and add it this many times, okay, the loop is going to go around b to the n times. How many people see what I'm saying? Okay, people don't see what I'm saying. Okay? So what does it cost to do multiplication by repeated addition? Okay? If I'm multiplying 15 times 3, repeated addition is what? It would be 3 plus 3 plus 3, or it could be 15 plus 15 plus 15, right? Now, the loop here is going around 3 times. Does everybody agree with that? But if I now make this thing 33, it's going to go around 33 times. If in general it's going to be an n-digit number, and it's going to be written in base b, this loop could go around b to the n times. Okay? That's where the exponent comes from. Does everybody see that now? So repeated addition is actually an exponential algorithm. This is interesting. It's exponential in the number of digits. Okay? It's not a question of n cubed or n something like that. That's why multiplication is an important thing and why the Romans eventually died out. Okay? Because this is the difference between a polynomial time algorithm and an exponential time algorithm. Okay? Any questions? Does anybody know how fast you can multiply numbers together? In fact, there is an algorithm that is n log n. That's a divide and conquer algorithm. And I believe there may even be, I think there may even be one that's faster than that. Something like n log n or something, but don't quote me on that. But there are more advanced ways to multiply, okay, than doing it this way. Okay? Any questions here? Okay? Fair enough. So that's how my multiplication works. Okay? And like I said, in my case, I implemented a shift operation to slide the numbers back and forth, which is multiplying by 10, which was relatively easy. Okay? And I did it by basically using repeated addition on a digit level, which didn't change the complexity of it because my digits were really constant size. But if they were not a small constant, it would have been a performance hit here. Any questions? That was my digit shift. Don't worry about that. Actually, how do you do exponentiation? Quickly. Suppose I want to compute the number a to the n. What is the right way to compute a number a to the n? Okay? I could do it by multiplication n times. Does everybody agree with that? If so, how many multiplications would I be doing? That would be basically n times the actual cost of the multiplication. What is the cost of n multiplications going to be? Okay? Probably a little bit hard to think about, but why is it hard to think about? The multiplication of an n-digit number times an m-digit number, we agree would be order nm. The problem is every time we do the multiplications, the digits are getting bigger. Does everybody agree the number of digits are increasing? We multiply a times a squared times a cubed times a fourth, right? But this would be n of those large numbered multiplications. Does everybody agree with that? How could we do that more efficiently? We want to compute a to the n. What's a faster way to compute a to the n? What? By noting that a to the n has the property that a to the n is a to the floor of n divided by 2 times a to the n minus 2 times n mod 2. What does this mean? If I interpreted this, if we have 5, what is 5 div 2? That's going to be 2, right? In integer arithmetic, the floor of it. That's going to be a to the 5 is equal to a to the 2 times a to the 2 times a to the remainder of 5 mod 2, which is 1, right? Does everybody agree that a to the 5 is a to the 2 times a to the 2 times a to the 1? The neat thing about this, though, is here, if we compute this once, this is only one more multiplication. It's it times itself. Does everybody agree with that? I've halved the exponent by doing only a constant number of multiplications instead of n mod 2, instead of n over 2 multiplications. Does everybody agree with that? So how many multiplications will this take to compute a to the n? Something like log n, right? Because what is log n? It's how many times do you have something, okay, before it gets down to 1. So doing this, I can only get away computing a to the n in only a logarithmic number of multiplications, which is an interesting thing. Any questions? Can anyone show me a faster way to compute a to the n? What is the fastest way to compute a to the n? Okay. Something involving logarithms and exponents? Okay. But by using your numeric library, how could you compute a to the n?
Log a, first evaluate log a and then multiply 10 and then
X is equal to log of a.
Yeah.
And you would say y is equal to
n multiplies x.
n
Multiplies x.
times x.
Yeah.
And then what are you going to do? Z is going to be equal to the anti-log, right? Which is the x function. This is in principle constant time. Why is this not a good thing to do, though?
Because what maybe dealing with integers.
Here you're no longer dealing with integers, right? You're dealing with floating point numbers, okay? And so that's really what the difference is here. You would lose precision doing it this way. Any questions? Okay, that's enough about arithmetic. Let's talk about the problems quickly. Okay, because there are 4 actually kind of interesting problems this time. First one is a problem called reverse and add. Actually, in reverse and add, what you're going to be told is there's an interesting property of the integers that holds for a lot of integers, which is if you take an integer and you reverse its written in base 10 and you reverse its digits and add it to itself. You take an integer, it eventually, you add it together, you get another integer. That's not so interesting. But if you take it and reverse it again and add it to itself, for most numbers, it seems, you eventually get down to a palindrome. What is a palindrome? Has anybody ever heard of a palindrome before? What is a palindrome?
A string which is same as the reverse.
Forward and backwards. Does anybody have a favorite palindrome?
Canal Panamas.
Okay, the one that you're saying is a man, a plan, a canal, Panama. That is a word string that it reads the same forwards and backwards. 9332 is an integer that reads the same forward and backwards. Basic what? Okay. The question is starting with an integer, you have to keep adding it to its reverse until you get a palindrome. Okay? Or it tells you to give up. Any questions? That's the first problem. The second problem, actually, archaeologist's dilemma. This is actually kind of interesting. Here you're given a bunch of numbers that are supposed to be powers of 2. Only you're not actually given the first thing. The claim is some alien civilization wrote out the powers of 2. What are the powers of 2? 2, 4, 8, 16, 32, 64, 128, 256. But the claim is that years of weathering ate up a lot of those digits. And the question is, find out what is the smallest power of 2 that starts with these digit sequences. Okay? So what's it say? Basically, here, given the number 2, what is the smallest power of 2 that will start with the number 2, digit 2? Okay? Where it has other digits to be that were erased. When you got to 256, 256 started with 2. 256 is 2 to the 8th. And that's what this is asking for, right? So read the problem. It involves computing powers of 2 and looking at what the early digits are. Any questions about that? Okay. Another one, ones. Okay. Basically says it gives you an integer, and I want to know what number do I have to multiply it by to get a number that is all ones. Okay. So to be precise, let's say we take a look at this thing. What's 111? Is 111 a prime number? No. What is 111? How do you factor it? 3 times, I think it's 37. Is that right? So if you were given the number 3, there is a 2-digit number that when you multiply it will give you all ones. Everybody agree with it? An interesting property of the integers is that any integer, when you multiply it by the right digit number, will give you all ones. Okay? Your goal is to find out which number is that and tell us how many digits long that number is. Okay? So you got to make a question. You'd like to make a number that is all ones, that is divisible by this, and the smallest one. And you'd like to know how many digits there are, how many ones there are with that property. Any questions? Okay, so read that. The final problem involves a game where you've got two sides and they're trying to realize a target number. Let's say that there's a target number of, 173. You and I are going to take turns if I'm playing against you. We start out with 1. You propose a number, a digit from between 2 and 9 to multiply it by. I will propose a digit to multiply it by. And the first person to drive it above the target, do they win or lose? Okay? It states so here, basically. The winner is the first one to reach the big number. Okay? So the question is, what number should you pick? To what number should I pick? So that each of us is trying to become the first number to get a number at least this big. Okay, what is the strategy we employ? Any questions about that? Okay, read the problems. Here I think they are logically of greater complexity than what we have dealt with before, at least in general. These are now dealing with math. They're no longer dealing with purely programming issues. So they'll require a little bit of thinking, and we're going to talk a little bit about the strategies for dealing with them next time. Any questions about that? Okay. Any questions? If not, get working on it. Thanks for your attention, and we'll talk about these problems in group. Read through the problems before next class, because I definitely did not explain them clearly enough that you all understand them at this point. Read through them and try to solve them. Okay, thanks a lot.